Hello and welcome back to Calculus 1, section 3.9 on derivatives of exponential and logarithmic functions, and then the logarithmic differentiation as well in all of its glory. So we'll start with derivatives of exponential functions because you already know pretty much everything you need to know for that. One formula which I stated earlier was that the derivative of e to the x is e to the x. And then we said that pretty much that's never the case, that e to the x floats around. Well, generally we had e to the ax to give us a e to the ax in a derivative. So these are the formulas that were presented to you earlier, and you memorize these formulas and you use them. Well, now with the development of chain rule from last class, you guys have access to a better formula, and this is the formula that is pretty much used all the time, so red. Instead of having a linear function in exponent, see this ax is almost as good as mx, right? We can say, well, how about we put any function? It doesn't have to be just x or ax. It could be maybe x squared or a cosine or whatever. It doesn't matter, just some kind of function there. And the answer to that would be, well, we use the chain rule. Derivative of e is itself, so e to the fx, times the derivative of f of x. So this is actually the formula that you will be using most of the time. So that's the formula, and it's just a simple chain rule that we have from previous lecture, right? You're just multiplying the derivative by the chain. But see, all of these formulas that we have here are, let me just put these arrows over here, say, yeah, this is what we pretty much use all the time. That's the important stuff. But see, each of these formulas that I have on the page so far, they all have e in the base. But can we have number 2 in the base, or number 6 in the base, 13? And the answer is yes, right? So if you want the general case, right, or what I call the most general case, right, you would have to not use e to the x, but b. So the derivative of b to the f of x. So now you can have 3 raised to sine, and you'll be fine. All right? The answer over here is b to the f of x times f prime of x times ln b. Now I'm not going to box this formula with a big with a highlighter, because it's actually rare to see a function, 3 to the x or 3 to the sine x. That's very rare. So this formula you're not going to use that much. But the one on top, you are going to take physics and engineering courses. The top formula is your life. Okay? So 95% or more of the derivatives are going to be in the pink box, and then the other whatever percent remains would be the either black box or some of the basics, on top. So we are focusing on the one in the purple box, pink box, because that's the one that it's most used. So what is the derivative of e to the sine x using the pink box, obviously? So if you follow, please note, when you're reading the formula, just look at the components of the formula. E to the f of x, that's the same. It's Control C, Control V, right? Copy and paste. So you get to copy this as is times cosine, and you're done. So the answer is quickly e to the sine x times cosine x. Exponential functions are one of the best functions to differentiate and integrate. So when you go to Calc 3, you will see a lot of exponential functions everywhere, because first, they show up in nature a lot, and second, they're a joke in comparison to some other things that you might run into. So that's the story of exponential functions. You will find this in population models, right? We talked about population briefly in the class. You have a population model. You have some kind of decay model for mass, whether it's radioactive or garbage or whatever it is, the carbon dating, to figure out how old something organic is that you dug up. All of these things have exponential function, and you can take the derivative of those exponential functions and then calculate the rate of change, the instantaneous rate of change. So you can figure out how many people were added in a particular year, how much mass was lost in a particular year, let's say, or so, and so on. So these are the uses for these guys. Now let's talk what is this? Log, exactly. There we go. Logs. Logs. Actually, before we talk logs, let's do something else. 2 plus 3 is? 5. Thank you very much. And then we can recover 2 and 3 by saying 5 minus 3 is? 2. And 5 minus 2 is? Perfect. 2 times 3?
6.
6 divided by 3? 2. 6 divided by 2?
3.
3. Right, this is just a little bit of warm-up, right? Now, we go from addition to fast repeated addition. Now I can have fast repeated multiplication. So 2 cubed is? 8. Cube root of 8 is? 2. How do I retrieve 3? Do what? 8 to 1 over 3 is 2. That's just this. My question is how do I get equals to 3?
Oh, right. What is it? Log base 2 of 8?
Yeah. That's where they fall. In a grand scheme of things, log base 2 of 8 is 3. Do we see where logs belong? So what is log? It's a basic operation, like addition and subtraction. It's nothing special. Now, why do we discriminate against it? Well, A, awful people. 2, A and then 2. I just want to see if you're paying attention. It's the only operation that has letters. Okay, if you observe, everything else has a symbol. This one has letters. But essentially, over here you're combining 5 and 3 to come up with a 2. Over here you're combining 6 and 2 to get 3. Over here you're combining 2 and 8 and you're getting 3. Right?
Right.
It's just, you don't have a cute symbol for it. Right? It's 3 letters and all of a sudden, oh. So, logs are completing this arithmetic table of basic calculation. Logs are not functions. until the variable creeps in. Then it becomes function. But if variable creeps in any of the other ones, it becomes a function, right? Replace any of the values anywhere in the what I wrote in black, and you will get a function. If you go and replace this 5, you will have x minus 3. That's a linear function, right? If you go over here and you replace 3 with x, you get 2x, also a linear function. Over here, replace 8 by x, you get radical function, cube root of x, right? So when you replace 8 with x, you get logarithmic function, right? If you replace 3 with x, you get exponential function. None of these are functions. This is just basic arithmetic, basic calculations. And then you plug in an x, right, as a variable, and then it becomes a function. So we don't get to talk about logs and always think of functions. No, because logs actually just compute values. You can go and can say log 3 of 81. And this is just a computation. There is no function here, nothing to graph, nothing to do other than to compute and say, okay, this is log base 3 of 3 to the 4, 4 log 3 of 3, which is 4 times 1 equals 4. This is what you learn in pre-calculus. Do we see any variables? No, we don't see any variables. It's just a calculation which says that if you combine 3 with 81 in a log, you will get 4 as the answer. You can combine 3 and 81 in a different way. Here, 3 plus 81, and you will get 84. Perfect. That's okay, right? But it was a different operation than this one. So are we green on this? We better be green, otherwise the homework is going to be 3 to the 81 is equal to. I'm going to skip that one. Yes?
So is like 2 to the third, is that in base 2?
Yes.
Okay.
So now, when we clear that up, that logs are just basic calculations, right, arithmetic, then we can bump it up and say I can create a function log base a of x. And then we have this special log base e of x, which we are writing as ln x. And then we have another special log where we have no base, and that's base 10. And these are your ln button in a calculator and log button in a calculator. That's all it is. So ln is always with base e, and log without a base is always log 10, base 10. But then you say, what if I want to compute log base 6 of something? Well, we have formulas that are called change of base formula, so that you can convert the bases into ones that your calculator speaks. So if you have log base 6 of what number here? Or 14, whatever, doesn't matter. You would actually have to go and say log 14 divided by log 6, or ln 14 divided by ln 6. So this is known as the change of base formula, and we are using it so that we can compute the logs fast. Usually they have a lot of decimals, and you keep 4 decimals for precision purposes, but sometimes you run into a whole number, right? The answer, and it is what it is. So I have this, and the most important formula for logs is the conversion formula, so that you can actually solve equations. But then we have the 3 formulas for logs that we are actually going to use later for logarithmic differentiation. So what are the formulas that we want to focus on in this class? First, I'll list the two cute formulas. Log base A of A is equal to 1. Log base A of 1 is always 0. I call these two cute rules. Cute rules. There we go, cute rules. So when you have base and the value the same, an argument the same, then the log is equal to 1. And if you have a 1 over here with whatever base, the answer is 0. Now, the next formula is the conversion formula. Note that I'm writing this in red because this is the way you're going to solve all of the equations, which will pop up in chapter 4 and then go through other calc courses as well. Conversion. A to the B equals C converts into log base A of C equals B. So these are our conversion formulas, and I hope you can quickly chase this ABC with the example I had earlier that we all seen. You see how B is the exponent and it's 3, and you got B over there on the other side as, right, 3. You already seen change of base. Change of base, and change of base formula is that log AB, so that's any base and any argument, is going to be either log base 10, so I'm not writing any base, it's understood it's 10, or ln B over ln A. These are all buttons on your calculator, so you pick one or the other. Don't mix them, right? Don't mix math. So you're either using log all the time or ln all the time on your calculator to compute this. And now finally, we get to those three formulas that you must know, otherwise logarithmic differentiation is not going to work for you. And that is that log base A of xy is log base A of x plus log base A of y. So if you have two values multiplied inside the log, you get to split them, but you split with the addition. The next one, so that's number 1. Number 2 is the one with the subtraction. So log base A of x over y is log base A of x minus log base A of y. And finally, the last one is the one that deals with exponents. So log base A of x to the p is p log A of x. So the exponent just escapes, but it escapes as the multiplication. Now, why is this important? It's important. It's going to be important for our logarithmic differentiation, but before we dive into logarithmic differentiation, we have to learn basic derivatives of basic log functions. So here we go. Formula number 1, that it's rarely used, but it's used, is to say that the derivative of ln x is 1 over x. Note the use of ln, which means base is e. It's ln over there, so base is e.
Sorry, Professor, can I see 1, 2, 3 again? Sorry about this. Okay.
So this formula, derivative of ln x equals 1 over x, you are going to use, at some times here and there, because your function is rarely just ln x. we like composite functions, right? When you do the function composition between two different functions. And in this case, right, we have ln x, so we are going to have ln of f of x. And actually, this is my favorite derivative, because I should have written this in red, because this is the one that it's most frequent. So red, and there will be a pink box around this, so leave some space. The derivative of ln of any function, ln of f of x. Look how cool the derivative is. Equals, you put f of x as is in denominator and its derivative in the numerator. So whatever your function is, you get to copy it here, and then for the chain rule purposes, just take the derivative up and you're done. By far my favorite derivative. Most of your derivatives in sciences and later courses are going to be these ones, right? ln of a function. And then we have another formula, which is the most general case, and that one would be when you have any base, you know, not just e, because these formulas are ln, which means base is e. But can we take the derivative of log base 2 of sine x? And the answer is yes, we can, because we have this new formula here that will work for any base you put out there. So the derivative of log base b, right? B for base, of any function. So I hope that you see that this is the most general case. You can't go and generalize more than this. Because now you're not just allowing any function in here, like you did before, and not so much here. So it's not just you are allowing functions, you're also allowing for any base. So as I said, log base 2 of sine x, you can actually take the derivative of that. So what is the derivative? It's the same derivative. F prime of x over f of x, and then you just have your ln b in denominator as well. So this formula deserves the box, obviously, but that's not the formula that you will be using 90% of the time or 95% of the time. It's the one above that you use pretty much all the time. So, okay. You guys are going to practice on these. So what is the derivative of log 5 of cosine x? And what is the derivative of log 3 of x sine x? Whatever. To make it worse. It's called mathematical gymnastics, right? You can technically do anything.
Yeah, yeah. No, she's on. Okay, she keeps me. Yeah, later on I asked her. So, yeah. Thank you.
All right, so what do we have? We have cosine x. The derivative of cosine x is negative sine x. And then we also have ln 5. So what is this? This is simply negative tangent x divided by ln 5. That's all it is. The second one is a little bit evil because product rule, exactly. X times sine x is the product rule. So yeah, evil me, right? So what do? We have our x sine x ln 3 in denominator. And then the product rule. Copy the first, derivative of the second, plus copy the second, derivative of the first. There's nothing really you can simplify there. Just, not write that one. And technically that's it. So if you are able to deal with this, which is literally copy the function as is, follow with the ln of the base. Do you guys see that if you have ln of x, the formula actually applies because that's log base e of x? Do we see that? So you're looking for the derivative of that. The main formula would actually work because ln 3 would now be ln e, which is 1. And then you will have x in denominator and its derivative on top is 1. So just 1 over x, right? The only one that you really need here is just this general case, because the general case would reduce everything to... But we also have these other formulas that work a little bit faster. Let's see. So what is the derivative of, say, x cubed minus 2x plus 3 to the 4th power times the cube root of x squared plus 1 divided by sine x. Sine to the cube x. What is the derivative of that? Wow. I don't think that even if you flip the notebook sideways would fit in one line, but what do we have there?
Problem.
A problem, good. This is called mathematical gymnastics, like zero application to this mess whatsoever. But if we are looking at the derivative, like what do we have there? We have the quotient rule as the big boss, right?
Power rule.
And then you have the product rule when you have to take the derivative of the numerator. And then each one of these individually is chain rule, yes, power rule, chain rule, yeah. So you have 3 chain rules embedded in the product rule and the quotient rule. And to unwrap something like this would take a very, very long time. But there is something really, really cool about all of this. Now I'm going to sound like Morpheus. What if I told you that you can take the derivative of this mentally, and the result you write down directly without any work would be in factored form, ready to pick up in chapter 4? What if I told you that everything you learned in chapter 3 so far regarding those rules you can just disregard, because you can bypass all of the product rules and chain rules and quotient rules and never do any one of those ever? Yeah.
Let's do it.
Logarithmic differentiation. So just to understand the scope and insanity of this technique, its power, we can just write the derivative of all of this instantly without actually doing any work. So what is the derivative of this? Well, the derivative is, we copy everything as is, which is x cubed minus 2x plus 3 to the 4th, plus the cube root of x squared plus 1, divided by sine cube x, times, and there is this other part that we would have to learn how to get, and that part is going to be 4 times 3x squared minus 2 divided by x cubed minus 2x plus 3 plus 1/3 of 2x over x squared plus 1 minus 3 times cotangent x. That's what it is. So that's how you take derivatives. Now, if you are to go and take this derivative using the quotient rules and product rules and chain rules, you know, within a few days of simplifying algebra, you might end up at this answer. Cool, huh? Should we learn this stuff?
Yes.
Yeah, right? So where are my mental processes as I'm doing this? Pretty much still in reserve. I have to trace the expansion of logarithmic functions, and I have to be able to take a very basic derivative, because I hope that you can spot the pairing that those are the derivatives of each other. And that's where your ln kicks in, where you copy the function on the bottom and its derivative on top. Over here is hidden because this is cotangent is cosine over sine. You can also pick up these exponents. A 4, 1/3, and a cube. You can pick them up as well. You see that? Yeah. And then you're also picking up that these two were on top and they're both positive, and this one is on the bottom and that one is negative. right? So what have I used? I used these formulas here. I use these formulas to actually break everything apart. All of those exponents with a third and 1/3 and 3 and a 4, that's all this rule. Whatever was in the numerator obeys this stuff, both positive, and whatever was in denominator is a negative, combined with all of these. So if you are able to mentally do that, you are able to take any derivative, no matter how complicated it is. You can go back to all of your product rule, quotient rule problems, and literally stare down at those, and within 5 seconds have the actual answer to the question without writing anything down. So let's first see why and how this works, and then how you can practice these things if you want to get to that point where you can just mentally take any derivative pretty much instantly. Yes? That means you will know product rule for the test, but because of the curriculum, but your education doesn't end with Calc 1, so you can vent it after the final, I guess. I don't know, because certain standards say use product rule to solve, right? And then it's dragged, but it is, right? So let's have a simpler question. Say the derivative of x to the 4 times sine cubed x divided by 5th root of x squared plus 1. There you go. That's considered a cheap question to learn, for the learning purposes. So what am I going to do here? I'm going to assign the function inside to some y, and then I'm going to ln both sides, and I'm going to expand, and then I'm going to hit everything with the derivative, and we're done. So y equals x to the 4 sine cubed x over 5th root of x squared plus 1. And then I will ln both sides. And then we are going to expand everything and get 4 ln x plus 3 ln sine x minus 1/5 ln x squared plus 1. So these are the expansions, those formulas that we used. Note that all of the exponents are in front of ln's, because that x to the p becomes p ln x, right? So all of the exponents are in front of ln's, and you have the 4th exponent and the 3 and 1/5. And then all of the terms that were in the numerator are positive. All of the terms that are in the denominator are negative. That's also rules 1 and 2. Once you expand everything, you hit this with a derivative, and that derivative is clearly implicit derivative. So derivative of ln y is 1 over y dy dx. Remember, you have to follow with a chain if you take the derivative of y in respect to x. Now you see that 1 over y? That y is going to go on the other side as multiplication. That's all of this, guys. Remember how I copied the entire problem? That problem was labeled as y. So this y will eventually go to this side, and that's, you start every one of these derivatives by copying the original problem as is. Now what are my derivatives here? 4 times 1 over x plus 3 times sine x in denominator, cosine x on top, minus 1/5 x squared plus 1 in denominator, 2x on top. So now dy dx is equal to y times, and we have 4 over x plus 3 cotangent x minus 2/5 x over x squared plus 1. And now write in what y is, which is x to the 4 sine cubed of x divided by the 5th root of x squared plus 1 times 4 over x plus 3 cotangent x minus 2/5 x over x squared plus 1. That's the derivative. Is it in factored form? Sure it is. That's factors on a pile, and this cannot be simplified any further. That's it. So now what do you do in chapter 4? You take each one of these and you say it's equal to 0, not the denominator obviously. You set each one of the numerators equal to 0, you come up with numbers, and then those are critical numbers, and then you go from there. This is just a technique to take derivatives. Let's do a basic quotient rule problem. Like if we were learning this for the first time, quotient rule formula, you might have, let's say, sine x divided by x squared plus 3, or any exponent, doesn't have to be x squared, whatever. So what would you do with this? You would take x squared plus 3 and square it and then put it up there times cosine, right? You would do the quotient rule, and that would take time. Now remember what we have over here. Y equals sine x over x squared plus 3. And now we are going to ln both sides. And if you ln both sides, you can expand. So you have ln sine x minus ln x squared plus 3. And now you hit this with the derivative. 1 over y dy dx is equal to, sine goes in denominator, cosine goes on top, minus x squared plus 3 goes in denominator, 2x goes on top. Dy dx is equal to save a step, we know that y is equal to sine x, so sine x over x squared plus 3, I mean, times cosine x over sine x, that's the cotangent again, x minus 2x over x squared plus 3. That's the derivative. Now you would argue, that's not what I'm going to get from chain rule. I mean from quotient rule. And I will say, is your answer factored when you do your quotient rule? Right? This one is. So, how do you convert this now into chain rule? Well, simple. Just FOIL this in, get the common denominator, and you will have the same thing as if you did the quotient rule. So please, you can practice, right? The basic chain rule right there. The only one that it's a little bit tricky, as it appears in these, is e to the x. Because e to the x would kill the ln part for that term. So you have to be a little bit careful when dealing with e to the x. Let's talk about that with the product rule. The derivative of, let's say, x squared e to the x. And I want to do this, right? We can do the product rule. Copy the first derivative of the second, right? Please understand that, use right tools for the job. You know what logarithmic differentiation is? It's not even the sledgehammer. It's that jackhammer that you use to break the concrete, and then you know, break the foundation and everything else, and you find oil. Like that's what logarithmic differentiation is. Now, if you have a product rule for x squared times e to the x, you know, the little hammer will do, like, you know, the ping one, like this large. So, sure, you shouldn't be using logarithmic differentiation on this, but let's, because we can. Right? Y equals, the first time they say you shouldn't, it's immediately, yeah, I am. That's how I, unfortunately.
I love using a jackhammer to build cabinets.
Perfect. Or when they say on those IKEA packages, do not use power tools. Right? You can put the screw in, the whole thing is like confetti. So we have this ln y is equal to ln x, and then 2 in front, plus, and here is the ln e. X is the exponent, goes in front, and ln e is 1. So that's the little bit tricky part there that kind of doesn't work in a pattern for others if e to the x pops up. Because now you don't have the ln derivative there, you just have x. So now, when we hit this with the derivative, d dx, you will get your 1 over y dy dx is equal to, and now the derivative here is 2 over x plus 1. So dy dx is equal to y, and y is x squared e to the x, times 2 over x plus 1. So if you are to distribute this, you will find exactly the same answer that the product rule gives you. So this would be the end. It's factored, and simple to work with each one of these. You go x squared equal to 0, x equals 0, e to the x equals 0, no solution, and then the other one over here to give you something as well. Now, if you have done the product rule, let's do that in green. If you have done your product rule, d dx of x squared e to the x, you would say, okay, copy the first, derivative of the second, plus copy the second times derivative of the first. You can factor x e to the x and get x plus 2, right? I hope it's good. Yeah, much easier to say equal to 0 here than equal to 0 there. But look what you can do. You can steal one of these x's and multiply inside, and as soon as you do that, you get x e to the x times x and x cancels, 2 plus x. That's the same step. Just by stealing one x from the pile of x squared and distributing it in the parenthesis here, it kills the x in the denominator and 1 becomes x. And you get this, which is the same as this. You really have to sit down and practice these things if you want it, right? Again, don't use the sledgehammer if you don't have to. But when the sledgehammer is needed and necessary, sure, bring it on. So now that we've seen a few of these problems, I am again able to go back to the very first problem that I did and explain it for one more time now that you know all of this background. You know that when I make the inside the function equal to y, I will take the derivative of ln y eventually, which creates 1 over y, and then when you move y to the other side, you get y. This is the reason why the function is copied, as is, because you get y on the right-hand side. Now, again, I'm doing this mentally without writing anything down. What do I see over here? I see fourth exponent. If I have fourth exponent and I have ln in front, that 4 jumps in front. That means it becomes a coefficient here, of 4. And then I know that ln of this, the derivative is this on the bottom, its derivative on top. So I write its derivative of 3x squared minus 2 divided by itself, because it's always f prime over f. Same pattern here. What do I have? I have, well, it's plus first of all, because it's in the numerator. And then you have 1/3, because that's the exponent of cube root of 3 is 1/3. There's going to be ln there, right? So ln of x squared plus 1, look, x squared plus 1 copied, its derivative on top. So easy this pattern is. It's insanely easy. The only time when you actually have to, if you practice this for a few hours, the only time you have to stop and think a little bit is if you run into e to the x, because e to the x messes up the pattern. But the pattern is always copy the problem as is, times each one of the exponents become coefficients. The ones that are in numerator are all positive, the one in the denominator are always negative, and then put the function down, its derivative on top. Function down, its derivative on top. Function down, which is sine, its derivative cosine on top. Cosine over sine is cotangent. So that's how it's done. Any derivative in few seconds, bypassing all of the product, quotient, chain, everything that is there. Like that. So what kills the chain? The formula for ln, where the p from the argument goes as p in front of the ln. That killed all 3 chain rules like this. That log rule. You see that? And then the other formula for log, where multiplication of arguments splits into 2 additions, just killed the product rule, because what used to be a product rule of x times y, now it's addition of a plus b. It makes it easy. And then the quotient rule dies again, because the division of the 2 things goes. It's subtraction of the 2 things. And what's easier than to do derivatives of addition and subtraction? You just do it term-wise. You don't have to worry about the product rule, quotient rule, chain, or nothing when you are doing derivatives term by term. So this logarithmic differentiation clearly simplifies the entire process. And as I said, it's a pattern that you actually memorize by doing this long way. I did show 3 different problems done long way. But if you practice this enough, you should be able, for the next class, and I'm not joking, for the next class, you should be able to take any derivative like that without writing. And then when someone says, what do you know? You put the derivative there and say, all right, I can take the derivative of this mentally. And that takes care of that conversation. Right? Yes?
So you said e to the x kind of messes
with the pattern, yeah.
Here, yeah.
With the flow.
What about e to the ax? How would that factor in? Just the same way, but...
Yeah, it's the same way. It's just ln and e. They cancel each other. You see, if I had e to the ax over there,
right,
then that ax would go in front of the ln. Changes nothing.
Oh, okay, so the ax would just go...
Yeah, so if a was here,
right,
then that a will just go in front of this x along with it. It goes along with the right, for the right, and then it will be here, right? Any other questions, concerns? Bye.